Have you ever wondered what holds it all together? What invisible thread connects the simple act of a dropped key falling to the floor with the majestic, slow spiral of a distant galaxy? It's a question that has echoed through human history. The answer is both astonishingly simple and profoundly deep. It's physics. The very same set of rules that governs our everyday world also choreographs the grand cosmic ballet. These laws are written into the fabric of everything, from the smallest speck of dust to the largest supercluster of galaxies. This cosmic story is our story. It begins with a simple observation. An apple falls from a tree. A ball thrown into the air always comes back down. We feel a constant pull towards the ground. This force feels like a local rule. But what if it wasn't? What if the same force that pulls the apple is also tugging on the moon, the planets, the stars? This is the leap of imagination that changed everything. Imagine looking up at the night sky. You see the moon, a silent, glowing companion. It doesn't fall to Earth, nor fly into the void. It is forever falling, pulled by Earth's gravity while moving just fast enough sideways to miss. This elegant dance is the same force as the apple's fall. The universe has one set of laws, universal and unbreakable, that applies everywhere. We are part of this intricate physical machinery, subject to the same cosmic laws since the beginning of time. Let's talk more about this force. Gravity. You can't see it, you can't touch it, but you feel its effects every moment of your life. It's the silent, relentless force that gives weight to our bodies and holds the oceans in their basins. On Earth, gravity seems like a simple downward pull, but its true nature is far more grand. Gravity is the master architect of the cosmos. It is the sculptor that gathers wisps of gas and dust together over millions of years, crushing them under their own weight until they ignite into brilliant stars. Without gravity, there would be no stars, no planets, no us. Think about our solar system. It's a beautiful, orderly family of planets, moons, asteroids, all circling a central star, our sun. What keeps this family together? Gravity. The sun is incredibly massive, containing more than 99% of all the material in the solar system. Its immense gravitational pull reaches out across billions of kilometers, holding every planet in its orbital path. Each planet, from speedy Mercury to distant Neptune, is following a track laid out by the sun's gravity. It's a cosmic dance that has been going on for more than 4 billion years, all thanks to this invisible, persistent force. But gravity's influence extends far beyond our local neighborhood. Look deeper into space, and you'll see its handiwork everywhere. Gravity is what pulls stars together to form the immense star cities we call galaxies. Our own Milky Way galaxy is a swirling disk of hundreds of billions of stars, all held in a gravitational embrace. And even galaxies themselves are not alone. They are pulled into groups, clusters, massive superclusters forming a vast, interconnected web that stretches across the entire observable universe. Gravity is the ultimate organizer, building structure on every cosmic scale. Every atom in your body is gravitationally connected to every atom in the most distant star. How do we know any of this? We can't travel to distant galaxies or visit the sun's fiery surface. Our knowledge of the cosmos comes to us as messengers, tireless travelers that cross the vast emptiness of space to reach our telescopes. The most important of these messengers is light. The same light that streams from your lamp and lets you see is also a carrier of cosmic secrets. Every twinkle from a star, every faint glow from a nebula is a postcard from the past, carrying information about its origin. When you look at the sun, and please, never look directly at it, you are seeing light that left its surface about 8 minutes ago. It took that long for the light to travel the 150 million kilometers to Earth. When you look at the next nearest star, Proxima Centauri, you are seeing light that is over 4 years old. The light from the Andromeda galaxy, our closest large galactic neighbor, has been traveling for 2.5 million years to reach your eyes. You are not seeing it as it is now. You are seeing it as it was when early human ancestors were first walking the Earth. This fact is one of the most profound in all of science. It means that our telescopes are time machines. The farther we look into space, the deeper we look into the past. We can see galaxies as they were billions of years ago, when the universe was much younger. This allows us to piece together the life story of the cosmos, to watch how galaxies formed and evolved over cosmic time. Light is our witness to creation. It carries the chemical fingerprints of distant stars, telling us what they are made of. It reveals their temperature, their age, and how they are moving through space. By studying the properties of light, we have discovered incredible things. We have learned that the same elements we find on Earth are also found in the most distant stars. The light from a faraway star and the light from a candle flame follow the same rules. Let's return to that apple. When Sir Isaac Newton saw it fall, he didn't just see a piece of fruit. He saw a profound question about motion. Why did it fall straight down? Why didn't it fall sideways? Why didn't it fall upwards? His quest to answer this led him to formulate 3 simple laws of motion. These laws were revolutionary. They described not just how apples fall, from a rolling ball on a table to the planets orbiting the sun. Newton gave us the rule book for motion, and it works just as well on Earth as it does in the heavens. His first law tells us that an object will stay still or keep moving in a straight line at a constant speed, unless a force acts on it. This is called inertia. It's the reason you lurch forward when a bus suddenly stops. Newton's second law connects force, mass, and acceleration. The more massive the object, the more force you need. The third law is perhaps the most famous. For every action, there is an equal and opposite reaction. Newton's laws of gravity are brilliant, but they don't tell the whole story. For that, we needed another revolution in thought, this time from Albert Einstein. Einstein imagined gravity not as a force pulling objects together, but as a consequence of the shape of the universe itself. He proposed that space and time are not separate and absolute, but are woven together into a single, flexible, 4-dimensional fabric called spacetime. Think of spacetime as a stretched rubber sheet. If you place a bowling ball in the center, it creates a deep dip in the sheet. Now, if you roll a small marble nearby, it won't travel in a straight line. It'll follow the curve in the sheet created by the bowling ball, spiraling inwards. According to Einstein, this is what gravity is. The sun is like the bowling ball, warping the space-time around it. The Earth, like the marble, is simply following the curve. This idea makes astonishing predictions. One is that gravity can bend the path of light. This was confirmed during a solar eclipse in 1919, when astronomers saw that the light from distant stars was bent as it passed by the sun. Another mind-bending prediction is that time itself is affected by gravity. Time runs slower in stronger gravitational fields. The clocks on GPS satellites actually tick slightly faster. Scientists have to constantly adjust them to keep the GPS system accurate. The closer you are to a massive object, the slower time flows for you. Gravity stretches not just space, but time itself. Now let's push these laws to their absolute limits. Let's travel to one of the most extreme and mind-bending objects in the entire universe, a black hole. A black hole is what's left behind when a very massive star dies. Its core collapses under its own immense gravity, crushing matter down to a point of infinite density called a singularity. The gravity around this point becomes so powerful that nothing, not even light, can escape its grasp. It is a one-way trip. Anything that crosses its boundary, the event horizon, is lost from our universe forever. Imagine you are in a spaceship, cautiously approaching a black hole. From a safe distance, you watch a brave astronaut in another ship venture closer. As your friend gets nearer to the event horizon, something strange begins to happen. To you, their clock appears to tick slower and slower. As they reach the event horizon, they would appear to freeze in time, their image fading and redshifting until they disappear completely. But for the astronaut, the experience is very different. From their perspective, their clock ticks normally. As they cross the event horizon, there is no sign, no wall, no dramatic moment. They simply slip across the point of no return. Looking back, they would see the entire future of the universe flash before their eyes in an instant. The immense gravity of the black hole would stretch their body into a long, thin strand of atoms, a process grimly nicknamed spaghettification. Black holes are not just cosmic vacuum cleaners. They are cosmic engines. The supermassive black holes that lurk at the center of most galaxies, including our own Milky Way, play a crucial role in regulating the growth of the galaxy around them. As matter falls into the black hole, it forms a superheated, swirling disk that can shine brighter than all the stars in the galaxy combined. This intense energy can blast gas out of the galaxy, preventing too many new stars from forming. These monsters of gravity are not just destroyers. They are also creators and regulators, shaping the evolution of the cosmos. In the 1920s, the astronomer Edwin Hubble made one of the most important discoveries in the history of science. While studying distant galaxies, he noticed something strange about their light. The light from almost every galaxy was shifted towards the red end of the spectrum. This is known as redshift. Just as the pitch of a siren's sound gets lower as it moves away from you, the wavelength of light gets stretched, or redder, when its source is moving away. Hubble realized what this meant. Nearly all galaxies are moving away from us. But it was even more profound than that. He found that the farther away a galaxy is, the faster it is moving away from us. This is the signature of a uniform expansion. It doesn't mean we are at the center of the universe. Imagine baking a loaf of raisin bread. As the dough rises, all the raisins move away from each other. From the perspective of any single raisin, all the other raisins seem to be rushing away, and the farthest ones are moving the fastest. This is what is happening to our universe. Space-time itself is expanding, carrying the galaxies along with it for the ride. This discovery completely changed our understanding of the cosmos. If the universe is expanding now, it must have been smaller, denser, hotter in the past. If you run the clock backwards far enough, everything in the entire observable universe must have been crushed together into an incredibly hot, dense state. This is the origin of the Big Bang theory. The Big Bang wasn't an explosion in space, it was the explosion of space. It was the moment, about 13.8 billion years ago, when our universe began its epic journey of expansion and cooling. For a long time, astronomers assumed that the gravitational pull of all the galaxies would be slowing this expansion down. But in the late 1990s, observations of distant supernovae revealed the exact opposite. The expansion of the universe is not slowing down, it's speeding up. Something is pushing the universe apart, a mysterious anti-gravitational force that we call dark energy. We don't know what it is, but it makes up nearly 70% of the entire universe. So, we have a universe governed by physics, expanding at an accelerating rate, galaxies, stars, planets. But what is all this stuff made of? When we look around us, we see trees, rocks, water, people. We know that all this is made of atoms, which are in turn made of smaller particles, protons, neutrons, electrons. When we look out at the stars, they too are made of the same kind of matter. This ordinary, familiar matter seems to be what the universe is all about. But here comes one of the biggest surprises of modern cosmology. All the matter we can see, all the stars, galaxies, planets, gas clouds, makes up only about 5% of the total cosmic recipe. That's it. All of human history, all of life on Earth, all the shining stars in the night sky are just a tiny fraction of what's really out there. The vast majority of the universe is completely invisible to us. About 27% of the universe is made of something called dark matter. We know it's there because we can see its gravitational effects. It's the invisible scaffolding that holds galaxies and galaxy clusters together. Without dark matter, galaxies would fly apart. There isn't enough visible matter to provide the necessary gravitational glue. We don't know what dark matter is. It doesn't emit, absorb, or reflect any light. It passes through us, through the Earth, and through everything we know, as if we weren't even here. It is a ghostly presence, revealing itself only through its gravity. The rest of the universe, about 68%, is the even more mysterious dark energy, the force driving the accelerated expansion of the cosmos. So the cosmic recipe is roughly 5% ordinary matter, 27% dark matter, 68% dark energy. This means that 95% of the universe is made of ingredients we cannot see and do not understand. We live in a cosmos dominated by dark, invisible components. This is one of the greatest challenges in physics today, to uncover the true nature of the dark side of the universe and complete our understanding of what everything is made of. From the simple fall of an apple to the accelerating expansion of the universe, we have journeyed across space and time. We've seen how a single set of physical laws governs everything, creating a cosmos that is both orderly and full of surprise. Gravity sculpts galaxies. Light carries messages from the past. The very fabric of space-time can bend and warp. We've discovered a universe filled with mind-bending objects like black holes, dark matter, dark energy. So where do we fit into this grand cosmic story? The answer is both humbling and inspiring. We are not separate from this story. We are a direct product of it. The elements that make up your body, carbon in your cells, calcium in your bones, iron in your blood, were not created on Earth. They were forged in the fiery hearts of massive stars that lived and died long before our sun was born. When these stars exploded as supernovae, they scattered these newly created elements across the galaxy. Over billions of years, gravity gathered this stardust into new clouds of gas, one of which collapsed to form our solar system. We are, in the most literal sense, stardust. The universe is not just something out there to be observed, it is within us. The same physical laws that dictate the orbits of planets also govern the chemical reactions in our brains that allow us to think, to wonder, and to comprehend the universe itself. We are the universe's way of becoming aware of itself. Through our curiosity, our science, and our imagination, the cosmos is beginning to understand its own history and its own workings. We are its eyes, its ears, and its mind. So the next time you look up at the night sky, remember this cosmic connection. The same gravity that holds you to the Earth is holding the stars in their galaxies. The light from those distant suns is a message from the past, telling a story of cosmic evolution. And the atoms that make you who you are were born in the heart of a star. You are not just a spectator. You are an active participant in this epic story. You are a piece of the cosmos, awake and alive and privileged to be on this incredible journey of discovery. The story is far from over, and the greatest adventures are still to come.